Okay, thank you everyone for being here for my talk. My name is Jiasheng, and this is a joint work with Dr. Donald Rubin and Professor Morris and Professor Hongjing here. Before we start the talk, I'd like to spend a minute actually on thanking all the healthcare workers. I'm not really sure if there is any healthcare workers in the audience since, well, this is a theoretical statistic talk to me, but I do sincerely appreciate their effort for the past 8 months. This picture is actually Dr. Li Wenliang, who warned others about COVID-19 outbreak in the very beginning of the past and actually he passed away in the line of duty despite being misunderstood at first. So without him, our reaction might be much slower and went to an even worse situation. To me, he is always going to be honored. Okay, now maybe I should cut to the chase. As we are all aware of that the reproduction number, usually denoted as R0, has been long recognized as the most crucial quantity in the epidemiology study. For example, we can use it to measure the effectiveness of an infection control method, such as social distancing, which has been widely adopted in the pandemic. But by the definition here, it's a time-invariant quantity, which isn't suitable for the whole developing of the pandemic, right? So what do we do? A natural solution is we introduce the instantaneous reproduction number RT here, which we can think it as a stochastic process or maybe a time series, with RT being the reproduction number for a fixed time window T here. Now, there have been some existing methods and early attempts in the area. I mentioned some, but not all of the work. To start, in 2004, Willinger and Tinos actually introduced an estimator, which later being recognized as the forward-looking estimator. This is in the sense that it needs to have the whole data from day one to the present day in order to estimate RT for any day T in between. Later, Corey and his co-author developed a Bayesian approach online estimator and have been applied to COVID-19 data in a work by by Professor Lin Xihong's group. But as a comment article to this application paper, that Professor Lipstick criticized that Corey's method has been the backward-looking. There, of course, are other papers that not directly focus on the instantaneous reproduction number, such as the SIR model and also the gravity models here. But as our target is mainly on estimating the instantaneous reproduction number and also try to investigate the covariates effect size to the pandemic transmission. So we, at the end, adopt the Corey's method because it's really not easy to introduce covariates into those two later models. Also, if we look at here, for the SIR model, since there is a relation between the reproduction number and also the beta T and gamma T here, but it's a ratio structure, so there would be more uncertainty issues. Corey's basic idea is the transmission tree structure, which if we denote IT as the incidence cases diagnosed on day T, then the transmission tree structure assumes day T's incident cases follows a Poisson distribution, giving the knowing pre-days incident cases. And as one may notice, it resembles to the branching process, but being more general here. Besides, the transmission tree structure we inherited from Corey's idea, since we want to introduce the covariates and investigate its relationship to the target quantity. So like a latent process, we can easily just introduce a regression model in this form. But recall that regression model is only correct specified when we have all the covariates, which is quite impractical. So we hope to borrow information from the neighborhood of RT and make the best use of the continuity or maybe tendency, which intuitively that RT time series should have. So we proposed this time series model instead. Or more specifically, this is an AR model with exogenous terms. We have two parts of the parameters, one part as the phi, which related to to the AR structure, and the another part with beta here, which is the effect size. Now, the model we proposed belongs to the category of observational-driven model and resembles to the Poisson regression with time series embedded model considered in Ziegler and also Richard Davis here. But the key differences are, first, we have the transmission tree structure, which makes the model much more complex. Second, we added the white noise term here. This actually completely changed the whole estimating procedure. We added white noise anyway because we do believe there are some covariates that we don't have access to, but it's a trade-off between the model correctness and estimating procedure complexity. Of course, one can impose a distributional assumption on epsilon t, but we tried another way out. We're just seeking for the semi-parametric estimator and impose no distributional assumption. By the way, our estimator is also an online estimator, just like Corey's, and it can be forward-looking or backward-looking with just a tiny change in the procedure. Detailedly, our estimating algorithm started with some initial estimators for the RT here, like the MLE for RT up to, here might not be C, okay, up to a prefix the time point tau 0 here. And inside the iteration here, we should do one iteration step each day after your estimates catch up to the present day. Okay, inside the iteration, say it's at day I+1, then conditional on previous information and RT being estimated at the ith iteration, we can define the beta tilde and the R tilde accordingly. Now, as we can see here, the beta tilde and R tilde is not really an estimator, but rather just a function of the unknown parameter phi here. Next. Okay. Next, with these functions defined, we can actually using the profile likelihood to get an estimator for phi and just replace the earlier phi 0, phi 1 here to get an estimator for the beta and R. I just use AR1 as an illustration. Of course, you can extend it much general. And here for forecasting, it's also formulated very naturally. Maybe not focus on the details here, but sorry, it seems like some problem here. For the properties of our estimating procedures here, first, there is only one step of maximization. And luckily, it's globally concave, so which means the estimators is unique. Also, we have a stochastic bound obtained for the estimator. And of course, it can easily be extended to multi-county case, which is really suitable for studying the United States data. And also, it can be easily extended to the non-parametric models. Now, even though I have illustrated the estimating procedure, but and also to talk about the stochastic bound, but unfortunately, it's still far away from getting a limited distribution, which means we don't have a variance estimator. So in order to do that, we're just looking for to be more creative and looking for other methods here. There are some details I like to just skip here, but briefly speaking, that Peter Hall, Bowman, and Kuskin, they have developed something over the years that would help us to get a block type bootstrap performance inspection. And we can use those to get a confidence band or maybe a confidence intervals. Now, of course, the simulation would went well, and maybe this visualization would show much better. Here, the observation is said to be just 120 days. So it's relatively small, in my opinion. And as we can see for the Oracle case, the estimated went quite good. But most importantly, even for those two misspecified models, as we can see, it went also quite well for the estimation, which means our model has certain robustness. Now, I know this is what's important to everyone the most, which is application to the real data. So our data set contains 517 counties and data from February the 1st to July the 6th. We choose 5 covariates based on the heat map here, and the 5 covariates mostly are population density, social distancing practice, and the wet bulb temperature. Another two would be the elderly population percentage and also population percentage of diabetes. So here is the estimator we get out at the end. And for a quick peek at the estimate, one transparent but yet prominent information is the elderly population percentage, which is this part, actually have a significant impact on the instantaneous reproduction number, while the wet bulb temperature is one of the least effective covariates here. This confirms two widely discussed and accepted conjectures, which one conjecture that elderlies are the more suspected population, and the another one conjecture that COVID-19 will not disappear along with the upcoming summer, just like SARS did. Here, I want to emphasize, so even though I said the temperature will not affect the instantaneous reproduction number very much, but unlike the other covariates, it can actually accumulate the effect and making an impact for long run. Just when the temperature goes up, people tend to go out more and did poorly in social distancing. If we are able to hold the social distancing level at the phase 1, then with temperature goes up, we can actually, I have actually a picture here showing that we can see this is a prediction actually for the September the 1st on the different level of the social distancing. If we are able to keep the social distancing at a certain level, then with the temperature goes from the July the 6th to the September the 1st, you can see the long run effect can be much larger here. And I think without need to say, well, phase 1 is actually the most suitable choice here. Unfortunately, we are opening up much more. And also another thing I want to point out is, so here, there is actually an epicenter transfer, and it's from the northeast northeast US to the southeast US in the period of change. But the change here is mainly in the sense of how the COVID-19 is grossed up. Even for the southeast became the epicenter, as we can see at the same day that the northeast still have cases compared to here. But just later after, maybe like 10 or 20 days after, you can see as an epicenter, we predicted it would just get much worse here. So the instantaneous reproduction number, RT, can actually have certain type of forecasting functions here. So I have one or more 2 slides about how to make the prevention decision making. So I briefly talked about our method, and the only thing is we can use our predicted, the instantaneous reproduction number, and also our predicted, here NC is predicted case. We can use it to construct an ordinal utility function such that we can base on this utility function to making a decision. That would certainly be, well, more attractive to the policy level. Okay. So the last 2 part is about this discussion about some issues in our method, which talk about such like here is
your 5 minutes.
Okay, so I just want 1 slide. This is about the selection bias and herd immunity. Just I want to say there would be a certain way to improve our method quickly. Just a field change here with 1 term, and everything can be done. The later just my references here, and I'm really thank you everyone for being here for my talk. If there is any question, I'm happy to answer right now.
Awesome, thank you.
Thank you.
There's plenty of time for questions, so feel free to field questions here, or otherwise we can get started on the next presentation, and feel free to drop a question in the chat. I'll go ahead and field a question. Did you run into any data quality challenges in your work? And if so, how did you get around that?
Okay, I think this is a trick question. And as we all know that if the data is really poorly presented, then there is no way to get useful information. Fortunately for US, well, I mean, it's both disturbing, but fortunately, that right now we have more than 3 million cases in my data set, and up to today, like the August of 28th, we actually have more than 5 million data set, which means we can discard as many wrong data as we want. So for me, I just simply set a threshold such that for a county that have incident cases very low at a certain day, I just discard the county directly, or I maybe just cut a period of that county's data directly. Otherwise, I think there is no way to get around this issue.
Okay, great, thank you.
Yeah.
I did see there was a question posted in the chat. Did you do any animation?
I didn't do that, but I think this is, of course, on our list here right now, because we are still trying to fill in all the stuff we can think of.
Okay, I think we have time for one more question. I saw there was another one posted in the chat. So there's been work done characterizing branching tree structure of.
Sorry, I couldn't hear you clearly.
Can you hear me clearly now?
Yeah.
So there's been work done characterizing branching tree structure of transmission as heterogeneous spread with effectively different reproduction numbers. This has been studied since 2011. In the end, they use negative binomials. Can you comment?
Okay. I think for the, I'm not sure if we are talking about the theoretical part or just the simulation part, because when we're talking about a statistical model, if it's chosen negative binomial, I think it's fine. But for theoretical part, as far as I know, when we're thinking about the branching process and allow each layer or each generation to having a different distribution, then of course there is not much work being done here. So it doesn't matter whether it's negative binomial or Poisson or any other distribution. It really didn't matter, because when we having the each generation changing, the constant directly would change the property, will change how the distribution looks like, and thereby we still would require certain moment condition to having an limiting distribution. As far as I know, it would definitely not converge to normal, and actually it would converge a mixture of the normal in a certain sense, and still with very strong conditions, very strong requirement about how the process going.
Okay.
This is okay.
Sorry, I have to interject. The next
Sure.
speaker should go, but feel free to explain in more detail in the chat.
Yeah, of course.